Hello everyone. Settle in, close your eyes and prepare for a journey. Imagine space. What springs to mind? Most likely, it's an endless, pitch-black void, an absolute vacuum, quiet and still, containing nothing but scattered stars and galaxies separated by unimaginable distances. This image is so deeply ingrained in our culture that it has become synonymous with nothingness. But what if I told you that this emptiness is one of the greatest misconceptions in the history of science? What if space is actually a vibrant, dynamic, and incredibly rich soup of particles, fields, and energies? In this lecture, we will venture together into the darkest corners of the cosmos to see what is hidden where we thought there was absolutely nothing. We will discover that the vacuum is not just not empty, but that it holds the key to understanding the most fundamental laws of creation. Get ready! Our journey into the non-empty void begins right now. To appreciate just how revolutionary the idea of a filled vacuum is, let's take a brief look back through history. For centuries, humanity struggled to grasp the nature of the space between celestial bodies. The ancient Greeks, for instance, couldn't accept the concept of absolute emptiness. Aristotle famously claimed that nature abhors a vacuum, and to explain how starlight reached Earth, the concept of the ether was proposed. This was envisioned as an invisible, all-pervading substance, filling all of space, serving as the medium for light to travel through, much like air serves as the medium for sound. The concept of the ether dominated science for millennia, lasting until the late 19th century. However, the famous Michelson-Morley experiment, conducted in 1887, failed to detect any ether wind, which should have been created by the Earth's movement through this medium. This failure, combined with the subsequent arrival of Einstein's special theory of relativity in 1905, which required no ether to explain the propagation of light, seemed to finally bury the old idea. The scientific world concluded space was indeed a vacuum, but as is often the case in science, history took an unexpected turn. By rejecting one outdated concept, we were only just beginning to approach a much more complex and astonishing truth about the nature of space itself. Let's begin our exploration by focusing on what lies between the stars within our own galaxy, the Milky Way. This space is called the interstellar medium. At first glance, it truly seems impossibly empty. If you take a single cubic centimeter of the air we breathe here on Earth, it contains about 25 quintillion molecules. That's a staggering number, followed by 19 zeros. Meanwhile, an average cubic centimeter of interstellar space holds just a single atom, one lonely atom. By Earth standards, this is a vacuum trillions of times thinner than anything we can create in our most advanced laboratories. This is precisely why, when we look up at the night sky, it appears as if there is nothing at all between the stars. However, the universe is vast, and even this negligible density, multiplied by the gigantic volumes of space between the stars, adds up to a colossal mass of matter. Scientists estimate that the total mass of the interstellar medium in our galaxy is roughly 10 to 15% of the mass of all its stars combined. If we could gather all that material together, it would form billions of new suns. This medium is not uniform. It consists of gigantic clouds of gas and dust that vary widely in temperature and density. Some of these clouds are cold and dense, while others are hot and diffuse. It is within these clouds, in this seeming void, that the nurseries of new stars and planetary systems are hidden. The interstellar medium is not merely a passive background for the stars. It is an active, dynamic, and vital component of the galaxy, involved in the continuous cycle of stellar birth, life, and death. Imagine the galaxy not as a mere collection of isolated stars, but as a huge, complex organism, where the interstellar medium functions as its circulatory system, transferring matter and energy. This is the first, and perhaps the most tangible form of filling the cosmic vacuum that we will examine. Let's dive deeper into the composition of the interstellar medium. Roughly 99% of it consists of gas, with the remaining 1% made up of tiny solid particles we call cosmic dust. The gaseous component itself isn't simple either. About 91% of the atoms in this gas are hydrogen, the simplest and most common element in the universe. Another 9% is helium. All other chemical elements, which astronomers jokingly refer to as metals, make up just a fraction of a percent. This gas exists in three primary states or phases depending on its temperature and density. The first phase is the cold neutral gas. It consists of hydrogen atoms where the electron is tightly bound to its proton. The temperature of these clouds is extremely low, ranging from just 50 to 100 degrees above absolute zero. That's approximately minus 223 degrees Celsius. These regions are known as HI regions. Since they don't emit visible light, they are very difficult to detect using standard optical telescopes. However, they give away their presence through a very specific radio emission. The electron in a hydrogen atom can exist in two energy states based on the orientation of its spin relative to the proton's spin. Occasionally, about once every 11 million years for a single atom, the electron spontaneously flips its spin to a lower energy level, emitting a radio photon with a wavelength of 21 centimeters. While this event is incredibly rare for an individual atom, these giant clouds contain so much hydrogen that the collective emission becomes detectable by radio telescopes. It is thanks to this 21 centimeter line that astronomers have been able to map the distribution of neutral hydrogen across our galaxy and reveal its spiral structure. These cold, dark clouds are vast reservoirs of raw material for future stars, patiently awaiting their moment in the interstellar void. The second crucial phase of interstellar gas is the warm ionized gas. Unlike the cold clouds, the atoms here have been blasted by intense ultraviolet radiation originating from nearby hot, young stars. This immense energy strips electrons from the hydrogen atoms, effectively turning the gas into plasma, a superheated soup of free protons and electrons. These regions are known as H2 regions, and they create a truly spectacular sight. When a free electron is captured by a proton, it cascades down the energy levels, shedding photons of light at every step. One of the most noticeable transitions in the visible spectrum is the H-alpha line, which imparts the characteristic and beautiful reddish hue to these nebulae. The most famous example of such a region is the Orion Nebula, visible to the naked eye as a faint, fuzzy patch within the constellation Orion. It is a giant bubble of ionized hydrogen surrounding a central cluster of young, massive, and extremely hot stars known collectively as the trapezium cluster. Their powerful radiation effectively illuminates the surrounding gas, causing it to fluoresce. Temperatures within these nebulae are drastically higher than in cold clouds, often reaching 10,000 degrees Celsius. These brilliant, glowing nebulae are, in effect, stellar nurseries in action. They are the exact locations where new stars are actively condensing from the interstellar medium. The intense radiation and stellar winds streaming off these newly formed massive stars compress the surrounding gas, triggering fresh waves of star formation in the adjacent areas. Therefore, the supposed void surrounding young star clusters is in reality a volatile and highly active environment where stellar energy is constantly reshaping the surrounding matter, giving rise to some of the most spectacular objects in the cosmos. These brilliant red beacons in deep sky photography serve as direct evidence. The cosmic vacuum is not only far from empty, it is capable of spectacular self-illumination. The third, and perhaps the most crucial phase of interstellar gas for our very existence, is molecular clouds. These are the coldest and densest regions of the interstellar medium. Their temperature drops to just 10 or 20 degrees above absolute zero, and their density can reach anywhere from hundreds to millions of particles per cubic centimeter. While this is still a profound vacuum by Earth standards, these are incredibly dense structures for outer space. It is in these extremely cold conditions that hydrogen atoms can combine to form H2 molecules. Besides molecular hydrogen, which is very difficult to observe directly, these clouds contain other, more complex molecules. Astronomers have detected traces of carbon monoxide, water, ammonia, formaldehyde, and even alcohols and simple sugars within them. To date, More than 200 different types of molecules have been identified in the interstellar medium, including those that are the building blocks for amino acids, the foundation of life as we know it. These molecular clouds appear in the sky as dark voids or patches because they are so dense that they completely block the light from the stars behind them. A prime example is the Horsehead Nebula in Orion, whose dark silhouette is visible against a backdrop of glowing red gas. But most importantly, these dark, cold clouds are the galaxy's primary star factories. Deep inside them, even denser clumps, protostars, begin to form under the influence of their own gravity. Gradually contracting and heating up, these stellar embryos eventually achieve the temperature and pressure required to ignite nuclear fusion, and a new star is born in the heavens. Our own solar system, including Earth and all of us, was born inside such a molecular cloud approximately 4.6 billion years ago. Thus, the darkest and seemingly most empty regions of the cosmos are in reality the most fertile. Now let's turn our attention to the tiny 1% of the interstellar medium that isn't gas. This component is cosmic dust. While 1% might seem insignificant, the role this dust plays in the universe is immense. Cosmic dust is not the household variety that gathers on our furniture. It consists of microscopic solid particles ranging from just a few molecules in size up to 1/10 of a micron, comparable, believe it or not, to particles found in cigarette smoke. They are primarily composed of silicates, which are similar to sand, graphite, various ices, such as water, ammonia, and methane, and complex organic compounds. So, where does this dust originate? It is forged in the atmospheres of cold red giants and supergiants, aging stars that continually shed their outer layers into space. Another critical source is supernova explosions, which violently eject heavy elements into space where they condense into tiny dust grains. This dust, scattered throughout the galaxy, has two pronounced effects on the light reaching us from distant stars. The first is known as interstellar absorption, or extinction. The dust grains effectively block a portion of starlight, making those distant stars appear fainter than their true luminosity. The second, and perhaps more intriguing effect, is interstellar reddening. Dust grains scatter shorter wavelength, blue light much more efficiently than longer wavelength, red light. This operates on the exact same principle that causes Earth's atmosphere to scatter blue sunlight, resulting in a blue sky and a red sun at sunset. The same process occurs in space. As starlight travels through cosmic dust clouds, it is stripped of its blue component, reaching our telescopes noticeably redder. This is precisely why astronomers must carefully account for both of these effects when calculating stellar distances and temperatures. But dust is far more than just an observational nuisance. It plays a foundational role in the formation of stars and planets. On the icy surfaces of these dust grains, hydrogen atoms find the necessary catalyst to combine into molecules, a critical first step in the formation of massive molecular clouds. Furthermore, within the protoplanetary disks surrounding young stars, these dust grains slowly stick and clump together, forming increasingly larger bodies called planetesimals, which ultimately evolve into planets, asteroids, and comets. Beyond the relatively calm gas and dust, interstellar space is constantly bombarded by streams of incredibly energetic particles known as cosmic rays. The name is a bit misleading, though, because they aren't rays in the traditional sense, but atomic nuclei accelerated to velocities approaching the speed of light. About 90% of these particles are protons, the nuclei of hydrogen. Roughly 9% are alpha particles, which are helium nuclei, and the remaining 1% consists of heavier elements, along with electrons and positrons. The energy these particles possess can be truly colossal, millions of times greater than what is achieved in the most powerful accelerators on Earth, like the Large Hadron Collider. When these primary particles strike Earth's atmosphere, they collide with air molecules, creating a massive cascade of secondary particles known as an atmospheric shower. These secondary particles are what we ultimately detect on the surface. But where do these cosmic speedsters come from? For lower energy particles, the primary accelerators are thought to be the shock waves produced by supernova explosions. When a massive star explodes, it ejects its outer layers at thousands of kilometers per second. This powerful shockwave propagates through the interstellar medium, picking up existing particles and repeatedly boosting their speed, like a surfer catching a massive wave. However, the origin of the highest energy cosmic rays remains one of the greatest enduring mysteries in astrophysics. Their energy is so immense that even supernova explosions seem insufficient to create them. Candidates for their source include active galactic nuclei, where supermassive black holes lie at the center of galaxies, or perhaps even exotic events linked to the decay of dark matter particles. These invisible, intangible particles continuously bombard our galaxy and our planet, forming another powerful and dynamic component filling what seems like empty space. They carry vast amounts of energy and significantly influence the chemical composition of the interstellar medium. So far, we've only discussed the space within our own galaxy, but let's zoom out to even greater scales. What actually fills the colossal voids between galaxies? This space is known as the intergalactic medium, or IGM. For the longest time, the consensus was that it had to be a virtually absolute vacuum. Galaxies are, after all, just tiny islands of matter in the vast, endless ocean of the universe. However, even here, we were met with a surprise. It turns out the space between galaxies is filled, though with material far more rarefied than the interstellar medium. This material is primarily hot, ionized hydrogen, and helium gas. The density of this gas is staggeringly low, on average less than 1 atom per cubic meter. But crucially, the sheer volume of this space is so colossal that, according to modern estimates, the intergalactic medium actually contains the majority of all the universe's ordinary, or baryonic, matter. That's more matter than is found in all the stars and galaxies combined. This matter forms a gigantic structure known as the cosmic web. Galaxies and galaxy clusters are not random points in space. They reside in the nodes of this web, connected by long, thin strands or filaments made of this intergalactic gas. Between these filaments lie the truly enormous, nearly empty regions known as voids. Detecting this gas is extremely challenging because it's so diffuse and hot that it emits almost no light in the visible spectrum. Scientists track its presence indirectly, observing how it absorbs light from distant quasars. As the light from a quasar, the single brightest object in the universe, passes through a cloud of intergalactic gas on its way to Earth, atoms in that cloud absorb photons at specific wavelengths. This leaves dark lines in the quasar's spectrum, creating what is known as the Lyman alpha forest. By carefully analyzing these lines, astronomers can map the properties and distribution of this otherwise invisible gas. This cosmic web is the foundational skeleton of the universe. It's a structure that first formed under the influence of dark matter's gravity, and then regular matter clung to it, eventually coalescing into the galaxies we see today. Thus, what was once considered the great emptiness between galaxies turned out to be filled with the most crucial building material of creation itself. Now let's journey back from the intergalactic depths closer to home and examine our immediate neighborhood. Even the space within our own solar system is far from empty. Our sun isn't just a static ball of gas. It constantly blasts a stream of charged particles, primarily protons and electrons, out into space. This flow is known as the solar wind. It travels at speeds ranging from 300 to 800 kilometers per second, filling the entire solar system. Near Earth's orbit, the solar wind's density is only a few particles per cubic centimeter, but its impact is immense. The solar wind is responsible for creating the stunning aurora when it interacts with Earth's magnetosphere. It's also what carves out the iconic ionic tails of comets, which always point directly away from the sun, regardless of the comet's direction of travel. This continuous stream of plasma creates a massive bubble surrounding the solar system, known as the heliosphere. The heliosphere is the region of space where the pressure of the solar wind dominates the pressure of the interstellar medium. It stretches far beyond Pluto's orbit, extending for more than 100 astronomical units. That's 100 times the distance between the Earth and the Sun. The heliosphere's outer edge, where the solar wind abruptly slows down as it collides with interstellar material, is called the termination shock. The Voyager 1 and Voyager 2 probes, launched back in 1977, crossed this boundary and are now in the region known as the heliopause, the outermost layer of the heliosphere, which is technically already interstellar space. The heliosphere acts as a protective cosmic cocoon for our solar system. It deflects a significant portion of incoming low-energy cosmic rays, shielding the planets, including Earth, from their harmful effects. So the vacuum within our own star system is actually a dynamic environment filled with solar wind and magnetic fields that form our very own cosmic shield. The cosmic vacuum isn't just filled with matter like atoms and ions, it is also permeated by various forms of radiation, or, as physicists call them, photons. The most fundamental and omnipresent of these is the cosmic microwave background, CMB radiation, often referred to as relic radiation. This is nothing less than the afterglow of the Big Bang itself, the faint echo of our universe's birth. For the first 380,000 years after the Big Bang, the universe was so hot and dense that it existed as an opaque soup of protons, electrons, and photons. Photons constantly interacted with these charged particles, meaning light could not travel freely. However, as the universe expanded and cooled, protons and electrons finally combined to form in neutral hydrogen atoms. This period is known as the epoch of recombination. Suddenly, the entire universe became transparent to light. The photons that filled all space at that exact moment were finally able to set off on a free journey, and they have been traveling ever since. Since then, the universe has expanded by more than 1,000 times. Due to this massive expansion, the wavelength of these ancient photons has been severely stretched. Originally, this radiation corresponded to a temperature of 3,000 Kelvin, a powerful glow similar to an orange star. Today, 13.8 billion years later, it has cooled down to just 2.73 degrees above absolute zero, and we observe it in the microwave range. This radiation reaches us from every direction across the celestial sphere with striking uniformity. On average, every single cubic centimeter of empty space around us contains 401 of these relic photons. This is the oldest and most distant light we can ever hope to observe in the universe. By studying the tiny temperature fluctuations in this radiation, which amount to just a few hundredths of a percent, cosmologists can learn an incredible amount about the early universe, its age, composition, geometry, and even the processes that led to the formation of galaxies. So the next time you see snow or static fuzz on the screen of an old analog TV, know that about 1% of that visual noise is created by photons born in the inferno of the Big Bang, having traveled across the void for almost 14 billion years. Let's talk about another fascinating set of particles, neutrinos. These astonishing, almost imperceptible particles literally stream straight through all of space. They are often called ghost particles, and for good reason. Neutrinos are elementary particles that carry no electrical charge and have a tiny, tiny mass, so small in fact that for a long time, scientists believed they were completely massless. Because of these properties, they barely interact with normal matter at all. Think about this. Every single second, day and night, approximately 65 billion neutrinos born in the thermonuclear furnace of our Sun pass right through every square centimeter of your body. And you don't feel a thing. To have a 50% chance of stopping even a single one of these solar neutrinos, you would need a lead shield 1 light-year thick. Neutrinos are created in various nuclear processes. Their main sources in the universe include thermonuclear reactions within stars, supernova explosions, and the interaction of cosmic rays with the atmosphere. There is even a background of relic neutrinos, the cosmic neutrino background, analogous to the cosmic microwave background left over from the Big Bang. These are even more elusive because their energy is incredibly low. While catching a neutrino is unbelievably difficult, scientists have developed giant detectors to do just that. These detectors are placed deep underground, underwater, or within ice sheets to shield them from background interference caused by other particles. For instance, the Super Kamiokande detector in Japan is a massive tank holding 50,000 tons of ultra-pure water, surrounded by thousands of sensitive photomultiplier tubes. Occasionally, very rarely, a neutrino will interact with an atomic nucleus in the water, generating a faint flash of light that the detectors register. Studying neutrinos opens a unique window into the universe. Because they interact so weakly, they can carry information directly from the densest, most inaccessible regions, like the core of the Sun or the collapsing heart of a supernova, places where even light cannot escape. These ghost particles are yet another fundamental component filling the cosmic vacuum and carrying within them the secrets of the most extreme processes in the universe. In 2015, scientists announced a discovery that rocked the world and ushered in an entirely new era of astronomy. For the very first time, gravitational waves had been directly detected. But what exactly are they? According to Einstein's general theory of relativity, massive objects warp the fabric of space-time itself. When these objects accelerate, especially during catastrophic events like the merger of two black holes or neutron stars, they create ripples, or waves, in this fabric. These disturbances then propagate outward in all directions at the speed of light. These waves are gravitational waves. They are not particles or radiation traveling through space. They are vibrations of space itself. As a gravitational wave passes through any object, it alternately stretches and compresses it in two perpendicular directions. However, this effect is unbelievably subtle. The gravitational waves detected here on Earth, originating from black hole mergers billions of light-years away, cause a change in distance thousands of times smaller than the diameter of a proton. To detect such infinitesimal oscillations, massive laser interferometers were constructed, such as LIGO in the US and Virgo in Europe. These facilities consist of 2-kilometer-long perpendicular vacuum tunnels through which laser beams travel. When a gravitational wave passes through the detector, it subtly changes the length of one arm relative to the other, which in turn alters the interference pattern created by the laser beams. This breakthrough has given us an entirely new way to see the universe. Gravitational waves allow us to observe the most extreme and dark objects that emit no light, such as black holes. Space-time, which we once considered a passive stage upon which cosmic events unfolded, has been revealed as a dynamic medium capable of rippling and carrying energy across billions of light-years. So the vacuum is not merely filled with matter and energy, it is itself an active participant in the cosmic drama, able to stretch, compress, and vibrate. Now we turn our attention to the most mysterious and dominant components of the universe, substances that undoubtedly fill the cosmic vacuum, yet whose true nature remains entirely unknown. Let's start with dark matter. Back in the 1930s, the astronomer Fritz Zwicky noticed something strange while observing the Coma cluster of galaxies. The galaxies within this cluster were moving so quickly that the visible mass of all the stars wasn't nearly enough for gravity to hold them together. The cluster should have simply flown apart. Zwicky hypothesized that there must be some hidden, invisible mass present in the cluster, which he dubbed dark matter. Later, in the 1970s, astronomer Vera Rubin discovered a similar anomaly while studying the rotation speeds of stars in spiral galaxies. According to the laws of physics, stars located on the outskirts of a galaxy should orbit the center much slower than the stars closer in, just as distant planets in our solar system orbit slower than the nearby ones. However, her observations showed that the rotational speed of stars at the periphery barely dropped off at all. The only possible explanation was that these galaxies were embedded in an enormous, spherical halo of invisible matter, which was generating the necessary extra gravity. Since then, a wealth of other indirect evidence for dark matter has accumulated, including gravitational lensing effects, analysis of the cosmic microwave background, and the large-scale structure of the universe. Today, we know that dark matter accounts for roughly 27% of the entire mass-energy content of the universe. This is about 5 times more abundant than all the regular baryonic matter, the stuff stars, planets, and we ourselves are made of. We know it neither emits nor absorbs light, and it only interacts with normal matter through gravity. but we have absolutely no idea what it is composed of. It cannot be made of the standard particles we already know. The leading hypotheses suggest it must be some new, exotic, as yet undiscovered particle, such as WIMPs or axions. Experiments are being conducted all over the globe, attempting to directly capture a dark matter particle, but so far they have been unsuccessful. This invisible substance forms the gravitational scaffolding that holds the entire structure of the universe together. It fills not only the space between galaxies, but the galaxies themselves, including our own. If dark matter is a puzzle, then dark energy is a puzzle squared. In the late 1990s, two independent groups of astronomers were studying distant type Ia supernovae to measure the expansion rate of the universe. These supernovae are crucial because they act as excellent standard candles. Since they all have nearly the same peak luminosity, we can use them to accurately determine cosmic distances. Everyone expected to find that the universe's expansion was slowing down due to the gravity of all the matter within it. Imagine their utter astonishment when they discovered the exact opposite. The universe is expanding at an accelerating rate. This finding was so unexpected that initially, scientists didn't trust their own results, but the data was undeniable. There had to be some mysterious force, a sort of anti-gravity, pushing space apart, causing galaxies to speed away from each other faster and faster. This hypothetical force was christened dark energy. According to current cosmological models, dark energy makes up a staggering 68% of the total mass energy density of the universe. It is the dominant component that determines the ultimate fate of our cosmos. But what is it? The simplest explanation is that dark energy is an inherent property of the vacuum itself. It is the intrinsic energy of empty space, often referred to as the cosmological constant. Quantum field theory suggests that the vacuum isn't truly empty. Instead, it is teeming with virtual particles constantly popping into and out of existence. These quantum fluctuations must possess energy, and this vacuum energy could manifest itself as anti-gravity. The trouble is, theoretical calculations predict a magnitude for this vacuum energy that is 120 orders of magnitude, that is, 1 followed by 120 zeros, larger than what astronomers actually observe. This represents the single greatest discrepancy between theory and experiment in the entire history of physics. There are other, more exotic hypotheses, such as the idea that dark energy is a new, dynamic field known as quintessence. Whatever its true nature, we know this mysterious substance is uniformly distributed throughout space and is its intrinsic characteristic. It dictates that in the distant future the universe is not destined for a gravitational collapse, but rather for eternal, accelerating expansion, an expansion that will eventually rip apart even galaxies and atoms. Finally, we arrive at the most fundamental and arguably the most counterintuitive aspect of the vacuum's fullness, the realm of quantum mechanics. On the microscopic scale, empty space is neither smooth nor serene. Instead, it transforms into a turbulent, seething froth known as quantum foam. This dynamic state is a direct consequence of one of the foundational laws of quantum mechanics, the Heisenberg uncertainty principle. This principle states that we cannot simultaneously know certain pairs of a particle's characteristics with absolute precision, for instance, its position and momentum, or its energy and lifetime. When applied to the vacuum, this implies that over incredibly short timescales, the energy at any given point in space can fluctuate wildly. According to Einstein's famous formula E=mc2, energy can convert into mass and mass back into energy. These brief energy fluctuations allow particle-antiparticle pairs to spontaneously burst forth from the void. These particles are called virtual, as they exist for too fleeting a moment to be directly observed. They spring into existence, survive for an instant, and then annihilate one another, returning the borrowed energy back to the vacuum. The more massive a particle is, the shorter its virtual lifespan. The vacuum literally teems with these virtual entities, electrons and positrons, quarks and antiquarks, and every other particle we are familiar with. Although they are virtual, their effects are undeniably real and measurable. A prime example is the so-called Casimir effect, where two closely spaced, uncharged metallic plates placed in a vacuum will attract one another. This happens because the gap between the plates limits the allowed wavelengths of virtual particles that can fit inside, while outside the plates there are no such restrictions. Consequently, the pressure exerted by virtual particles outside is greater than the pressure inside, creating a net attractive force. This effect was predicted in 1948 and has been experimentally verified. Thus, at its most fundamental level, the vacuum is not an absence of matter, but a genuine, dynamic, physical medium brimming with hidden activity. This is what constitutes vacuum energy, the same energy that, as we discussed previously, may be linked to dark energy, although this link presents enormous theoretical challenges. Let's turn our attention back to the interstellar medium and delve deeper into its structure. We've mentioned that it's highly heterogeneous, but the sheer scale of this complexity is truly astonishing. The galactic disk functions as an intricate ecosystem composed of gas at vastly different temperatures and densities, all locked in constant interaction. The model describing this environment posits the coexistence of several phases, generally existing in pressure equilibrium. The cold neutral medium, or CNM, which we've discussed, with temperatures hovering around 80 Kelvin, exists as dense clouds. While these clouds occupy only a small fraction of the volume, they contain a significant portion of the total mass. These clouds are embedded within the warm neutral medium, WNM, which is far more expansive but less dense, registering temperatures around 8,000 Kelvin. This medium consists of the exact same hydrogen atoms, but they are moving considerably faster. Next is the warm ionized medium, WEM. It has a similar temperature profile but is composed entirely of plasma. This WIM surrounds hot stars and accounts for roughly 1/5 of the disk's volume. But perhaps the most surprising component is the hot ionized medium, HIM. This is an extremely tenuous gas heated to temperatures of 1,000,000 degrees Kelvin. It's believed to be formed by the interaction and merger of supernova remnants. When a massive star explodes, it generates a gigantic bubble of superheated gas. This bubble expands, eventually merging with others, to create a connected network of tunnels and voids filled with this scorching hot phase. This hot phase occupies up to half of the entire volume of the galactic disk. Imagine a block of Swiss cheese. The dense cold clouds are the cheese itself, and the voids, the holes filled with that hot gas, are, well, the holes. This complex multi-phase structure is constantly cycling and changing. Stellar winds and supernova explosions inject immense energy into the ISM, heating the gas and forming new bubbles. Conversely, the gas cools by radiating energy, condensing back into denser clouds where new stars are born. This continuous flow of matter and energy, often referred to as the galactic fountain, sustains the life of the galaxy and underscores just how complex and dynamic the processes within the cosmic vacuum truly are. The cosmic vacuum isn't just filled with gas and dust, it's also permeated by magnetic fields. Although incredibly weak, hundreds of thousands of times less powerful than Earth's magnetic field, they operate on galactic scales and play a crucial role in countless astrophysical processes. Scientists believe the galactic magnetic field is generated and sustained by a dynamo mechanism, much like the one that creates our planet's magnetic field. The movement of conductive plasma within the galactic disk, specifically its rotation and turbulent flows, generates electrical currents, which in turn produce the magnetic field itself. This field consists of both an organized component, which generally traces the galaxy's spiral structure, and a chaotic, turbulent component. These magnetic fields exert a massive influence on the interstellar medium. First, they dictate the motion of charged particles. Ions and electrons in the interstellar plasma cannot move freely across the magnetic field lines. Instead, they are forced to spiral along them, effectively beading onto them. This fundamental constraint affects how gas flows and mixes throughout the galaxy. Second, the magnetic field exerts pressure that helps prevent massive gas clouds from undergoing gravitational collapse. During the star formation process, the magnetic field is crucial. It can slow the contraction of a protostellar cloud and helps siphon off excess angular momentum via powerful bipolar jets. Magnetic fields are also intrinsically linked to cosmic rays. It is the fields that contain the cosmic rays within the galaxy, forcing them to follow complex spiraling paths. Without this magnetic containment, cosmic rays would simply escape into intergalactic space. In a reciprocal relationship, cosmic rays moving through the interstellar gas create pressure that actually stretches and inflates the magnetic field. Detecting these faint fields requires specific methods. One approach is observing synchrotron radiation, which is emitted by high-energy electrons, a component of cosmic rays, as they spiral in the magnetic field. Another key technique relies on the Faraday effect, the rotation of the polarization plane of radio waves from distant sources as they pass through magnetized plasma. Thus, these invisible magnetic fields are yet another crucial player, structuring and filling the cosmic void. We've previously mentioned the complex organic molecules discovered within molecular clouds. This field of study, known as astrochemistry, has yielded an astonishing array of discoveries over the past few decades. It turns out that the cold, dark depths of interstellar clouds are surprisingly efficient chemical factories. Chemical reactions under these conditions proceed very differently than they do here on Earth. Low temperatures and densities mean that gas phase reactions happen extremely slowly. The key player here is cosmic dust, which we discussed earlier. The icy mantles on the surface of these dust grains act as catalysts, providing a site where atoms and molecules can meet and react. Ultraviolet radiation that penetrates the cloud can break down molecules into active radicals, initiating entire chains of chemical transformations. The result is a striking diversity of compounds. Beyond simple molecules like water, ammonia, and methane, researchers have found alcohols, methanol, ethanol, aldehydes, simple sugars, glycolaldehyde, and even precursors to amino acids, such as aminoacetonitrile. One of the most intriguing discoveries is the detection of polycyclic aromatic hydrocarbons, or PAHs. These are large, flat molecules, similar to soot particles, formed from linked benzene rings. They are believed to be extremely widespread, potentially accounting for up to 25% of all the carbon in the interstellar medium. These molecules efficiently absorb ultraviolet light and re-emit it in the infrared spectrum, playing a crucial role in regulating the thermal balance of the interstellar environment. The most exciting aspect of these findings is that all these complex organic compounds, synthesized in the depths of space, are then incorporated into newly forming stars and planetary systems. Comets and asteroids that bombarded the young Earth might have delivered these building blocks of life to our planet, spurring the formation of biological molecules. Therefore, the chemistry occurring in the apparent void between the stars may be directly connected to our own origins. Let's take another look at cosmic rays and how they interact with matter. Even though their overall density is incredibly low, the energy carried by each individual particle is enormous. This interaction leads to crucial consequences. When a high-energy proton or helium nucleus from a cosmic ray collides with an atomic nucleus in the interstellar gas, such as carbon or oxygen, a process called spallation occurs. This violent collision essentially shatters the target nucleus into smaller fragments. This is how rare, light elements like lithium, beryllium, and boron are created. These elements are almost never formed via stellar nuclear fusion. On the contrary, stars efficiently burn or destroy them, even at relatively low temperatures. The vast majority of these elements in the universe, including the lithium found in our phone batteries, were created precisely by these high-speed collisions in interstellar space. The observed abundance of these elements in the atmospheres of old stars and in meteorites perfectly matches the predictions of cosmic ray spallation models. This offers yet another elegant confirmation that space is not a static void, but a dynamic environment where active processes constantly reshape even the chemical composition of the universe. Furthermore, cosmic rays are the primary source of ionization within dense molecular clouds. Ultraviolet light from stars cannot penetrate deep into these clouds, but energetic cosmic rays pierce right through them, knocking electrons out of molecules and creating ions. This ionization, while weak, plays a critical role in the chemistry and dynamics of these clouds, primarily because ions are what link the neutral gas to the surrounding magnetic field. Without cosmic rays, the formation of stars and planets would proceed entirely differently. In summary, these invisible travelers, hurtling through the vacuum, exert a direct influence on the most fundamental processes within the galaxy. As we've discussed, the intergalactic medium holds the vast majority of the universe's baryonic matter. But exactly where is it, and what state is it in? For a long time, this uncertainty was known as the missing baryon problem. When astronomers calculated all the visible matter, the stars, galaxies, and cold gas, they accounted for only a fraction of the baryons predicted by Big Bang models and cosmic microwave background observations. The majority of ordinary matter simply seemed to be lost. The solution to this mystery began to emerge in recent decades, thanks to observations made in the X-ray and ultraviolet spectra. It turns out that a significant portion of these missing baryons exists as extremely hot and diffuse gas, filling the vast filaments of the cosmic web and the halos surrounding galaxies. This environment was dubbed the WIM, short for the warm-hot intergalactic medium. Its temperature ranges from 100,000 to 10 million degrees Kelvin. At these extreme temperatures, the gas is highly ionized, radiating primarily in the soft X-ray and far ultraviolet ranges. This composition makes it notoriously difficult to detect. Scientists believe this gas was heated by shock waves generated during the formation of the universe's large-scale structure, as matter violently collapsed into the gravitational wells of filaments and clusters. Detecting the WIM became possible by observing the absorption lines of highly ionized atoms, such as oxygen-6 and oxygen-7, in the spectra of distant quasars and blazars. These observations confirmed that the filaments of the cosmic web are indeed filled with this hot gas. Thus, the seemingly empty space between galaxies is actually filled with gigantic, invisible reservoirs of plasma, which account for the universe's missing matter. This discovery underscores how our understanding of the cosmos is constantly evolving as we develop new instruments capable of probing its previously invisible components. We've previously talked about the cosmic microwave background, the relic photons left over from the Big Bang, but there is an analogous background composed of other particles. Theoretically, this must include the cosmic neutrino background, or CMB. Just like the photons, neutrinos in the early universe were in thermal equilibrium with the rest of the matter. About 1 second after the Big Bang, as the universe cooled to 10 billion degrees, the interaction between neutrinos and matter became so weak that they effectively decoupled and began to propagate freely. These relic neutrinos should still fill the universe today, maintaining an extremely low temperature of about 1.9 Kelvin. Their predicted density is massive, approximately 336 neutrinos of each type per cubic centimeter. The challenge is that their energy is minuscule, far lower than that of solar or atmospheric neutrinos. This fact makes direct detection using current technologies virtually impossible. Nevertheless, their existence is confirmed indirectly. Though faint, these neutrinos contribute to the universe's overall energy density and influence processes in early cosmic epochs, such as Big Bang nucleosynthesis, the formation of light elements, and the eventual shaping of the CMB itself. Precise measurements of fluctuations in the CMB and the large-scale distribution of galaxies allow us to set constraints on the properties of these neutrinos. These findings align extremely well with the predictions of the standard cosmological model. If we ever manage to directly register these particles, it would be a monumental triumph for physics. It would open a window into the very first second of our universe's life, an era inaccessible even to observations using relic photons. This invisible ocean of ancient particles is yet another layer of reality hidden within the cosmic vacuum. Let's take another trip back to our solar system, but instead of viewing it from the inside, we'll look at it from the outside. The boundary where the heliosphere interacts with the surrounding interstellar medium is a highly complex and dynamic structure. The Sun isn't stationary, it barrels through the local interstellar cloud at roughly 23 kilometers per second. This motion generates a kind of bow shock ahead of the solar system, much like the wave created in front of a supersonic jet. Interstellar gas and dust flow around the heliosphere, but crucially, not all particles are stopped. Neutral atoms, like hydrogen and helium, which are immune to magnetic fields, can penetrate deep inside the heliosphere. Once inside, they are ionized by solar ultraviolet radiation or through charge exchange collisions with solar wind particles. They then become what scientists call pickup ions. While these ions are subsequently swept away by the solar wind, heading back into space. By studying these neutral atoms and pickup ions using missions like IBEX, the Interstellar Boundary Explorer, we can literally peek beyond the edges of the solar system and characterize the properties of the ambient interstellar medium. IBEX maps the boundaries of our solar system by detecting high-speed particles called energetic neutral atoms, or ENAs. These ENAs are created right at the heliopause and stream back toward Earth. This data revealed that the interaction between the heliosphere and the interstellar medium is far more complex than scientists had anticipated. It uncovered a mysterious, gigantic ribbon in the sky, a region where the flux of these neutral atoms is dramatically enhanced. This clearly demonstrates that even our cosmic home is not an isolated island. Rather, it is in constant, complex dialogue with the galactic environment that surrounds it. This boundary is not just empty space, but an active, turbulent plasma laboratory where two worlds, the world of the Sun and the world of the galaxy, are constantly colliding. The space within our solar system isn't just filled with matter and radiation arriving from deep space, it's also populated by the products of its own evolution, specifically the zodiacal dust cloud. If you ever find yourself under truly dark skies far removed from urban light pollution, you might witness a subtle, pyramid-shaped glow just after sunset or before dawn. This faint light stretches upward from the horizon along the ecliptic, the visible path the sun traces across the sky. This phenomenon is known as the zodiacal light. It is simply sunlight scattered by microscopic dust particles that orbit the Sun primarily in the same plane as the planets. This cloud, more commonly called interplanetary dust, is composed of particles ranging roughly from 10 to 300 microns in size. Where does all this dust originate? Its primary sources are comets, which vaporize as they near the Sun, leaving long trails of dust and gas, as well as continuous collisions between asteroids in the main belt located between Mars and Jupiter. While the cloud's density is incredibly low, far thinner than the vacuum achieved in the best laboratories on Earth, its immense extent means there is enough material to produce that visible glow. These tiny dust grains aren't permanent. Due to the effects of solar radiation and solar wind, a process known as the Poynting-Robertson effect, they slowly spiral inward, eventually falling into the Sun. This perpetual decay means that a constant resupply of new dust from active comets and asteroid fragments is essential to keep the cloud sustained. Occasionally, Earth's orbital path takes us directly through particularly dense streams of this cometary debris. When this happens, we witness meteor showers, often popularly called shooting stars. Every streak of light we see is a tiny fragment of interplanetary dust burning up upon entry into our atmosphere. Thus, even the seemingly empty void between the planets in our solar system is actually filled with this fine, constantly replenished dust, a residue that produces one of the most beautiful and subtle displays in the entire night sky. So far, we've discussed matter and energy that we can either measure directly or whose presence we can infer from our observations. But there are also more hypothetical, yet theoretically possible ways to fill the vacuum. One of these is connected with the so-called primary black holes. These are a hypothetical type of black hole that, unlike conventional ones formed by collapsing stars, might have originated in the very early universe, within the first second after the Big Bang. At that time, the density of matter was so immense that even minor density fluctuations could have triggered gravitational collapse and the creation of black holes. These primary black holes could have ranged widely in mass, from the size of an asteroid up to thousands of solar masses. Those smaller than a mountain's mass should have already evaporated by now, thanks to Hawking radiation, a quantum process through which black holes slowly lose mass. But more massive primary black holes could have survived to the present day, freely traveling throughout the cosmos. For a long time, they were considered one of the leading candidates for dark matter. After all, they are invisible, composed of standard matter, yet they don't participate in nuclear reactions or form luminous structures. However, numerous observations, particularly searches for gravitational microlensing events, where such an object passes in front of a distant star, briefly magnifying its brightness, have placed very strict constraints on the total number of these objects. Today, it is widely believed that primary black holes cannot make up the bulk of dark matter. Nevertheless, some quantity of them may certainly exist and contribute to the overall mass density. Finding such a solitary, wandering black hole traversing the void remains one of the most challenging tasks for astronomers. This is yet another example of how the vacuum might conceal the most exotic objects imaginable. Considering the cosmic vacuum, we cannot ignore the concept of inflation. This is the hypothetical period of ultra-fast, exponential expansion of the universe, believed to have occurred within the very first fraction of a second after the Big Bang. The theory of inflation was proposed in the early 1980s to solve several fundamental issues with the standard Big Bang model. Specifically, it addressed the horizon problem. Why distant regions of the universe that couldn't possibly exchange information share the same temperature, and the flatness problem. Why our universe is so remarkably close to Euclidean geometry. According to this theory, in a minuscule amount of time, roughly from 10 to the -36th to 10 to the -32nd seconds, the universe increased its size by a factor of at least 10 to the 26th power. To put that in perspective, an area smaller than a proton swelled up to the size of a grapefruit. So, what caused the universe to expand so dramatically? It is hypothesized that this was a peculiar state of the vacuum known as a false vacuum. This state possessed immense energy density and powerful negative pressure, effectively acting as anti-gravity. This state was unstable. At the end of inflation, the field responsible, called the inflaton field, decayed. Its energy was then converted into the hot, dense soup of ordinary particles and radiation, marking the beginning of the familiar hot Big Bang phase. But the most fascinating aspect is that the quantum fluctuations of this inflaton field during inflation were also stretched to astronomical scales. These microscopic fluctuations became the seeds from which, under the influence of gravity, all the structures we observe today emerged: galaxies, galaxy clusters, and the entire cosmic web. We see the imprint of these primordial fluctuations as tiny temperature variations mapped in the cosmic microwave background radiation. In summary, the entire visible structure of the universe was born from the quantum fluctuations of empty space during the very first moments of its existence. This is perhaps the most profound and astonishing illustration of just how non-empty and vital the vacuum truly is. Let's turn our attention back to cosmic dust and its surprisingly dynamic properties. We traditionally thought of it merely as a passive absorber of light, but recent discoveries show it's far more active than we imagined. For instance, interstellar dust grains have been observed rotating at staggeringly high speeds, sometimes billions of revolutions per second. This theoretically predicted effect is known as nanoparticle rotation. Scientists believe this extreme speed is caused by the grains interacting with starlight photons and stray gas atoms. This rapid spinning can lead to the emission of microwave radiation, which often acts as a confusing or contaminating signal when astronomers study the cosmic microwave background. Moreover, rapidly rotating dust grains that possess an electric dipole moment can also generate faint electromagnetic radiation. Another fascinating phenomenon is dust grain alignment. The long, elongated grains found in the interstellar medium aren't just chaotically distributed. They have a distinct tendency to orient their long axes perpendicular to the lines of the galactic magnetic field. This alignment causes the polarization of light from distant stars. As starlight passes through a cloud of this organized dust, the component of light polarized parallel to the grain's long axes is absorbed and scattered more strongly. Consequently, the light that reaches us is predominantly polarized in one direction. By measuring this polarization, astronomers can map the geometry and strength of the galactic magnetic field. While the exact alignment mechanism isn't fully clear, a leading theory suggests it involves radiative torques, a moment of force generated when photons interact with asymmetric dust particles. Essentially, these tiny vacuum-borne particles act like microscopic compasses, charting the direction of invisible magnetic fields and helping us unlock yet another secret regarding the structure of our galaxy. Let's take a look inside the largest, emptiest regions of the cosmos, cosmic voids. These are gigantic bubbles, hundreds of millions of light-years across, which are almost entirely devoid of galaxies. Voids occupy most of the volume of the universe, while galaxies and their clusters are concentrated in the thin walls and filaments that surround them. For a long time, voids were believed to represent truly absolute emptiness. However, recent research suggests that they are not entirely vacant. First, they still contain some matter, both dark and baryonic. It's just that the density is far lower than the cosmic average. This sparse environment can hide extremely small, faint, dwarf galaxies that are notoriously difficult to detect. A few such void galaxies have been identified, and they are of great interest because their evolution unfolded in near total isolation, free from the powerful influence of large neighbors. Secondly, voids are permeated by magnetic fields. While their precise origin and strength are debated, observations of gamma rays from distant blazars suggest that intergalactic space, including the voids, must contain faint magnetic fields. These fields may have been generated in the early universe or ejected from galaxies via stellar winds and active galactic nuclei. Thirdly, voids serve as ideal laboratories for studying dark energy. Because the gravitational influence of matter within them is minimal, the accelerated expansion effect caused by dark energy should manifest there most purely. By studying the weak gravitational lensing of light from distant galaxies against the backdrop of voids, scientists can obtain independent estimates of dark energy's properties. Thus, even the most desolate landscapes of the cosmos contain vital information about the fundamental laws of nature and the hidden components of our world. It turns out that emptiness helps us understand fullness. We've discussed virtual particles as a manifestation of the quantum nature of the vacuum. But there's another related phenomenon with observable consequences: vacuum polarization. According to quantum electrodynamics, or QED, when a strong electromagnetic field is present, the vacuum itself can behave like an optical medium. This occurs because a photon can briefly fluctuate into a virtual electron-positron pair. If this fluctuation happens within an intense external field, say near a highly magnetized neutron star or a magnetar, that external field will influence the virtual electron and positron, causing them to become polarized. This, in turn, affects how other photons propagate through that region. Specifically, the vacuum becomes birefringent. Photons with different polarizations will travel at slightly different speeds. This effect is incredibly subtle and extremely difficult to measure. However, in 2016, astronomers observing a neutron star located 400 parsecs from Earth were able to detect the signature of this phenomenon for the very first time. They observed a high degree of linear polarization in the visible light emanating from the star, a finding that could only be explained by that light passing through the highly magnetized vacuum surrounding the object. This striking discovery offers direct confirmation that empty space can indeed be altered by intense fields, validating the predictions of quantum electrodynamics even under these extreme cosmic conditions. This fundamentally blurs the line between emptiness and matter, demonstrating that the vacuum is a complex, polarizable medium whose characteristics can be dynamically altered. It is not merely a passive backdrop, but an active participant in physical interactions governed by the laws of the quantum world. Cosmic strings represent another exotic, yet theoretically possible inhabitant of the cosmic vacuum. These are hypothetical, one-dimensional topological defects thought to have formed during phase transitions in the early universe. To understand this, imagine water freezing. As ice crystals form, they may have different orientations. Where these crystals meet, defects, or tiny cracks, arise at the boundaries. Something analogous may have happened within the vacuum of the early universe. As the cosmos cooled, it likely underwent a series of phase transitions associated with the symmetry breaking of fundamental interactions. If symmetry was broken differently in distinct regions of space, stable topological defects could have formed at their boundaries. Depending on the type of symmetry breaking, these could manifest as zero-dimensional defects, monopoles, one-dimensional defects, strings, or two-dimensional defects, domain walls. Cosmic strings, if they exist, must be unbelievably thin, narrower than a proton, yet possess enormous mass per unit length, creating a correspondingly powerful gravitational field. They could stretch across truly enormous distances, perhaps spanning the entire observable universe. Such strings would necessarily leave specific observational signatures. For instance, they might act as gravitational lenses, producing duplicate images of distant background objects. They would also be a potent source of gravitational waves. Furthermore, a moving cosmic string should leave a distinct trace in the cosmic microwave background, CMB radiation, appearing as an abrupt, straight temperature discontinuity. To date, no convincing evidence of cosmic strings has been found, placing stringent constraints on the theories that predict their existence. Nevertheless, they remain an intriguing possibility. If we were to discover even a single such string, it would provide a direct window into physics at super-high energies unavailable in any particle accelerator. It would also prove that the vacuum has a complex topological structure, retaining relics from the very first moments of the universe's existence. As we explore the sheer diversity of what constitutes the vacuum, we must confront the very notion of nothingness. In contemporary physics, absolute nothing is an immensely complex and arguably even a meaningless concept. As we've established, even if we strip away every particle, all known radiation, and every field, we are still left with space-time itself. General relativity reveals this to be a dynamic entity. It can curve, expand, and vibrate. At the quantum level, this space-time is teeming with virtual particles and energy fluctuations. It might be that space-time itself, along with the laws of physics that govern it, are fundamental properties of reality, meaning a state lacking them is simply unattainable. There are even hypotheses such as the theory of cosmological natural selection, which suggest that universes might be born from black holes within other universes. During this process, the underlying laws of physics might subtly change. The universes that survive are those whose laws facilitate the creation of the maximum number of black holes. In such a model, there is no room for absolute nothingness, only an eternal process of cosmic birth and evolution remains. A different approach, linked to string theory and M theory, posits the existence of numerous dimensions beyond our standard 3 spatial and 1 temporal dimensions. Our universe, in this view, might be nothing more than a 3-dimensional brane floating within a higher dimensional space called the bulk. In this scenario, the vacuum of our universe is merely a local feature within a vastly more complex multidimensional structure. All these concepts, of course, remain highly speculative, yet they dramatically illustrate how far modern physics has moved beyond the intuitive, common-sense notion of emptiness. What we call the vacuum turns out to be one of the most complex and enigmatic entities in nature, holding the fundamental keys to the origin, evolution, and ultimate fate of our cosmos. Let's turn our attention back to something more tangible and examine how this cosmic environment directly impacts us and our technology. We've already mentioned that the heliosphere and Earth's magnetosphere protect us from cosmic rays and solar wind, but this protection is not absolute. The most energetic cosmic rays can penetrate the atmosphere and reach the Earth's surface. They are capable of causing electronic malfunctions, particularly in computer chips and satellite systems, leading to what are known as single-event upsets, or SEUs, where a charged particle flips the state of a memory bit. This poses a significant challenge for aviation and aerospace engineering. Furthermore, cosmic rays are a major source of radiation exposure for airline crews flying at high altitudes, and even more so for astronauts in orbit. When planning long-duration interplanetary missions to Mars, for example, radiation shielding against galactic cosmic rays is one of the primary technical hurdles we must overcome. Solar flares and coronal mass ejections, CMEs, which are essentially amplified manifestations of the solar wind, can trigger geomagnetic storms. These storms can disrupt communication and navigation satellites, interfere with radio signals, and even lead to widespread power outages here on Earth by inducing powerful currents in power grids. The most famous example is the so-called Carrington event in 1859, when an exceptionally powerful geomagnetic storm caused telegraph systems to fail across all of Europe and North America. If an event of that magnitude were to happen today, the damage to our technological civilization would be catastrophic. Thus, the perceived emptiness of space around us is not merely a background, it is an active environment we must account for and protect ourselves from. As we wrap up this deep dive into what is clearly not an empty void, let's take a moment to survey the complete cosmic landscape. We began with the interstellar medium, the tenuous yet massive component of our galaxy. It consists of gas in every imaginable phase, ranging from the frigid molecular clouds where new stars ignite to the searing hot plasma that inflates supernova bubbles. We saw this medium shot through with microscopic dust, which obscures starlight but acts simultaneously as a catalyst for forming complex molecules and the very building blocks of future planets. We learned about the unseen torrents of cosmic rays, accelerated to incredible energies, fundamentally altering the chemical makeup of the cosmos. We then ventured beyond our galaxy, finding the cosmic web, a gigantic filamental structure of gas where the vast majority of all ordinary matter is ultimately contained. We realized that all space is permeated by the cosmic microwave background, the enduring echo of the Big Bang, and by those ephemeral, hard-to-catch neutrinos. We grasped that even space-time itself is not static. It can vibrate, transmitting gravitational waves generated by the most violent cosmic cataclysms. Then came the grandest puzzles: dark matter, the invisible scaffolding of the universe, and dark energy, the mysterious anti-gravity force aggressively pushing space apart. And finally, at the most fundamental level, we discovered that the vacuum is a churning quantum foam, teeming with virtual particles that wink in and out of existence. This comprehensive picture stands in stark contrast to the simplistic image of a silent black void. The cosmos is a complex, multi-layered, and supremely dynamic system, where every component, from microscopic particles to entire galaxy clusters, is locked in continuous energetic interaction. The realization that the vacuum is not empty is more than just a curious scientific footnote. It represents a fundamental shift in our entire worldview, allowing us a much deeper comprehension of how our universe operates, and crucially, what our true place is within it. So, our long journey through what we once perceived as empty space is drawing to a close. What exactly have we learned? We have come to realize that the idea of an absolute void is nothing more than an illusion. The vacuum of space, far from being empty, has proven to be an incredibly rich and complex place. It is filled with the gas and dust from which stars are born and die. It is permeated by invisible fields and streams of particles carrying colossal energy. It holds the very light of creation in the form of the cosmic microwave background radiation, and even where there seems to be absolutely nothing, space itself is teeming with activity on a quantum level, its fundamental properties shaping the ultimate fate of the entire universe. But perhaps the most profound takeaway is this: over 95% of the contents of this vacuum, dark matter and dark energy, remain a complete mystery to us. We can observe their gravitational effects and we can measure their quantity, yet we have no idea what they truly are. The greatest breakthroughs in cosmology over the last few decades have ultimately led us to an awareness of our deepest ignorance. But this is not a cause for despair, quite the opposite. It is a source of immense inspiration. It means that the most breathtaking discoveries are still ahead of us. Thank you for spending this time with me, delving into the mysteries of the cosmos. I hope this lecture helps you relax and drift off to sleep, filling your dreams with stars, nebulae, and the deep enigmas of the universe. If you enjoyed this journey, please subscribe to the channel and hit the like button. And in the comments below, let me know which of the contents of the cosmic vacuum surprised you the most. Good night.